All right, everybody, we'll just give it a couple of minutes just to see people are still joining. All right, it looks like the rate of people joining the room has slowed down. So welcome everybody. Can I just check that you can all see and hear me okay? All right, in that case, welcome everybody to the second of the Applied Networking Research Workshop sessions for 2022. My name is Colin Perkins from the University of Glasgow. I'm pleased to be chairing this special session on protocol specification techniques. So I'd like to begin with the usual reminders. The Applied Networking Research Workshop is organized by ACM SIGCOMM and by the IETF, and it's co-located with the IETF meeting, as you all know. And as a result, that means we follow the IETF's intellectual property rights disclosure rules. So by participating in this meeting, you follow the rules, which I'm sure you're all familiar with. You agree to follow the rules which I hope you are all familiar with, and that if you're speaking at the microphones and you know of any patents or intellectual property that covers the topic you're discussing, then you agree to disclose that. And the links on the slide point to the detailed policies there. In addition, this session is being recorded and will be available online on YouTube after the session. And if you speak at the microphones in the room, if you join the session remotely, then you agree to being recorded and you agree to that recording being made publicly available. In addition, if you're participating in person and you're not wearing one of the red do not photograph lanyards, then you consent to appear in the recordings and in the photographs of the session. And online participants, if you unmute your microphone and turn on your camera, again, you may be recorded and the recording may be published. And as I say, this recording is being published, is being recorded, and I believe it's also being live streamed. Any personal information you give to the IETF, to the IRTF, will be handled in accordance with the privacy policy, and there's a link to that on the slide. That mostly applies to your registration details. And by participating in the IRTF, you agree to work respectfully with the other participants, and you agree to follow the code of conduct. If you have any questions or concerns about that, please either contact me or contact the Ombuds team, and the link with the contact details for the Ombuds team is on the slide. And a final reminder before we start, because of the risk of COVID, as a safety measure, we are requiring all in-person participants in this meeting and in the other IETF controlled areas of the meeting venue to wear N95 or equivalent masks at all times while they're in this meeting or in the IETF controlled areas. The only exception for that is for the speakers in the session who are actively giving the talks at the front microphone. If you're making a comment or asking a question from the floor microphone, we do ask that you remain masked at all times, and we ask that you remain masked while you are in the meeting at all times. Okay, so this is the Applied Networking Research Workshop. The goal of the ANRW is to provide a forum for researchers, vendors, network operators, and the standards community to talk about, to discuss interesting new results in applied networking research. One of the goals is to try and find inspiration from the topics and the problems being discussed in the IETF, and the other is to try and connect the research community with the IETF and to help bring new ideas into the IETF community, into the standards community. The goal is to encourage this two-way exchange of ideas. The ANRW is very much there to encourage, hopefully, the submission of new research results that could form the basis of engineering work in the IETF, but also to help better specify internet protocols, possibly change operational practices, possibly influence future research and experimentation in the IETF and the IRTF. One of the key areas there, I think, is or one of the key goals for the workshop is to think about how we can better specify internet protocols. And a lot of this has been in the form of ideas for new protocols themselves. I mean, as we saw in the talks this morning, as we've seen it in the previous versions of this workshop, we've had a lot of talks about how to specify new protocols, about new protocol designs, improvements to protocols, and so on. Part of the discussion, though, I think, is not what new protocols we might need or how to improve protocols, but how to specify protocols. That's something we haven't discussed so much in the ANRW, and which I think is one of the goals of this session, is to try and to start to think about how we describe and specify protocols. How we can, to think about how we can specify, how we can ensure that the protocols we're specifying are consistent and correct, and how we can verify that the specifications we are writing as researchers or as engineers in the IETF are correct, and how we can validate if the implementations match those specifications. I think one of the key goals of writing a specification is to communicate in a way that we know that what is written in the spec is correct, and that we can check that the implementations match that specification, check that the specification is self-consistent, the implementations match the specification, and everything should interwork. The way we have historically done that in the IETF community, in the standardization community, has been, though, to use natural language. We write RFCs in English, and we use English prose to describe and specify the protocols. And yes, we occasionally use formal language, right? We've been using ABNF, for example, for longer than I've been involved in the IETF, which is far too many years. More recently, we've started using Yang in a lot of specifications, and there's a number of other languages sort of scattered around the RFC series. But predominantly, we specify RFCs in English. What I'm hoping we can start to do in the session is to start to discuss whether this is the right way of writing protocol specifications. And start to discuss to what extent formal methods, structured specification languages, natural language processing, or other techniques can help to describe network protocols. The goal is very much not to think about how we think about how RFCs are prepared. Right? There was what I hope was a light-hearted comment in the chat earlier about is this about whether we use Markdown or XML for writing RFCs. Right? The goal of today is not to start a conversation about the RFC series. The goal is to start a conversation about how we specify protocols in general, and whether English is the right way of writing these protocols, to what extent formal methods or other techniques should be incorporated. I'd like to use this session hopefully to start a conversation about how we specify protocols, and hopefully to begin to connect academic researchers who are studying protocol specification with the engineers in the IETF, the researchers in the IETF and the IRTF that specify protocol standards and that design and develop new protocols. So, our agenda for today. We've just finished the introduction and status updates, and then we have 3 invited talks. The first talk will be by Max von Hippel from Northeastern University, who'll be talking about automated attack synthesis by extracting finite state machines from protocol specifications. That will be followed by a talk from Jane Yen from USC, who'll be talking about some work they've been doing on tools for disambiguating RFCs. And then finally, Chris Wood from Cloudflare will be talking about some of the work that's been happening in the Crypto Forum research group and some of the successes and limitations of the way that group has been specifying cryptographic standards. And then at the end, we have, I hope, some time for discussion before we close. There is a notes, there's a hedge doc for notes. The link is on the slide here. If you have questions or comments, either put them in the chat or put them in the hedge doc. I guess probably better to put them in the chat. There's also a session in the hedge doc in the notes if you would like us to get in touch about any of this work. If you're interested in following up on any of these ideas, then please put your name in there, and we'll try and follow up afterwards. And we'll talk more about this in the discussion session at the end. So with that, if Max is present in the room, if he could come up, and I'd like to hand over to him for the first talk.
I'm here, so I'm ready to go. Should I use this microphone or the other one? Standing one, okay. All right. And okay, and Colin, can you give me control over the slides?
Yep, I'm just trying to find the right button in Meetup.
Got it. All right, thank you very much.
There we go, you got it? Okay, over to you.
All right, my name is Max von Hippel. I'm a fourth-year PhD student at Northeastern University, and today I'll be talking to you about automated attack synthesis by extracting finite state machines from RFCs, from protocol specification documents. This was a collaborative work with Maria Lenore Pacheco from Purdue, who recently graduated and is now a professor at University of Colorado Boulder, as well as her advisor, Dan Goldwasser at Purdue, another student from my lab, Ben Weintraub, and our advisor, Christina Niederrotaro. And this work was presented also at the IEEE Security and Privacy Conference. So today we're going to be talking, or at least I'm going to be talking, about automated protocol analysis. This is old news to those of you who build protocols, so everybody in this room, but the internet runs on protocols such as TCP, UDP, et cetera. And these protocols create a sort of shared language for computers to talk to one another. Here we have pictured the internet, or specifically the ARPANET, in December 1969. At the time, there were 4 computers talking to one another. The internet has grown considerably since that picture was drawn. I'm a formal methods researcher, and in formal methods, we call these things crypt-key structures. But to normal software engineers, protocols are described by finite state machines. And a finite state machine is actually a completely unambiguous specification of the language of a protocol. And essentially, when I say that a protocol makes it so that 2 computers speak the same language, I'm saying something both informal and formal. The formal statement is that they run either the same state machine or state machines that accept the same language. The informal one is that they know how to talk to one another. In our group at Northeastern, we specialize in studying these finite state machines, either using formal methods or other approaches, and trying to find flaws in them. So we take a protocol, we define a protocol to be whatever is in these RFC. We then formalize it using a finite state machine that we write in some language like Promella or UPAL or something like this. And then we have a tool that generates attacks against that protocol expressed as an Fsm. So there's kind of a lot of hidden steps in between there, right? Going from specification to Fsm to attacks. And I'd like to disambiguate that a little bit. When we talk about protocols, we first and foremost have to talk about RFC specifications, right? Which is obviously especially salient in this context. These are written by the IETF. They're written in English prose, which I think is the topic of today's conversation. And although they may seem technical to somebody who doesn't write these documents for a living, the reality is that they really could be quite a bit more technical than they are, right? So for example, they could be written in Coq or Agda. They could be written in a programming language if we wanted them to. And there are advantages and disadvantages to their current presentation. Then a programmer reads these RFC specifications and implements them. So on the left, we have a tiny little screenshot of the DCCP RFC. And on the right, we have a tiny little screenshot of DCCP implemented in the Linux kernel. And there are all sorts of decisions that the implementer has to make when implementing the RFC. And that doesn't just include decisions about how to implement some functionality, like, oh, this list needs to be sorted. Will I use, merge sort or bubble sort? But also decisions about what it is that the specification actually says in the first place. Because since it's written in English, that's not inherently clear. So when the implementer reads the RFC specification and decides what she is going to implement, implicitly, she's creating a mental model in her head. And to me, as a formal methods person, I view that mental model as a finite state machine. But it doesn't really matter. You could view it as any isomorphic thing. The point is that obviously a human being reading English text is going to imagine what that text is supposed to communicate. And that thing that she or he imagines is some expression abstractly of what they intend to implement. They then go and implement it, and hopefully there's no errors in that process either. So bugs in a protocol implementation can arise from any one of the steps in this process. First of all, there could be fundamental design flaws in the specification. It could be that we specified something that was bad, right? It was a bad idea, and the idea needs to be reworked. It's also entirely possible that the mental model, the finite state machine, is wrong. In other words, that the programmer or implementer made some mistake when she read the specification and misinterpreted something. Now, we could blame that on the programmer or blame it on the author. It doesn't really matter, but mathematically, there could be a discrepancy between the finite state machine that the programmer intends to implement and the one that was abstractly described by the protocol text, by the RFC. And then finally, it's entirely possible that the specification is great and the finite state machine that the programmer imagines is great, but the programmer has a typo or something, and so there's some bug in the implementation, which was unintended, right? So the programmer writes something that does not do what she intended to do. This last class of bug is an extremely well-studied problem, and there are a ton of really great techniques for approaching it, and it does not interest me today. So we will be talking about the other two. So this presentation is going to focus on fundamental issues with protocol design and ambiguities and omissions in the specification. The first half of this presentation will be about how we can automatically extract a finite state machine from a protocol specification. So I'm going to take an RFC document and I'm going to automatically guess or extract a finite state machine that should represent that RFC. This is sort of like automating the first step that the implementer does when she reads the specification and tries to decide what it says before she goes and implements it in Rust or Go or whatever. The second half will be doing something useful with that. So in order to measure that the extracted finite state machine is actually good for something, I'm going to do something with it. And by something, I mean attack synthesis. I'm going to automatically generate attacks. If you're in this room and you're like, well, that sounds cool, but I don't care about security, I'll tell you right now, you can view these attacks as bugs. So you could also view it as I'm going to automatically find bugs. So this is relevant whether or not you care about security. So let's focus on the first part first, and then we'll move on to the second part. When we try to extract a finite state machine from a request for comments document, there are a number of critical challenges that we faced. First and foremost, there's simply no one-to-one mapping between the text and what we call as canonical finite state machine. In fact, it takes human expertise to read a RFC and interpret what it is that it says or should say for a number of reasons that we'll get into. Second, and related to the first point, RFCs contain omissions, mistakes, and ambiguities. Here's an example from the DCCP RFC, where a sentence, if interpreted mathematically, would imply the existence of a transition from part open to open upon receipt of a DCCP closed packet. But of course, that would be nonsensical. If you receive a DCCP closed packet, you should close your connection, not go to open. And so if you read the rest of the document, it becomes clear that that transition should not exist. But if you read this sentence and interpret it literally, it clearly implies the transition that isn't there. And I will tell you from now years of experience that RFC documents are riddled with sentences like these. Another problem is that off-the-shelf natural language processing tools are simply not suitable. Generally speaking, they are trained on newswire text or books or things like this that are non-technical in nature. And so they face the exact same problem that I face when I tried to describe my research to my girlfriend who's not a programmer, which is that I use all sorts of lingo that are kind of domain specific and don't mean anything to people in other fields, like in her case, biology. So we need something that's trained on relevant text, such as computer networking textbooks or Stack Exchange, Stack Overflow questions, etc. Finally, there's a ton of variation in the language and structure of different RFCs. And this is one of the, I think, interesting results we'll show today is that, spoiler alert, the DCCP RFC is more complicated than the TCP one, at least in terms of its English text. So we have a multi-step approach. The first step is that we create a technical language embedding. Essentially what we're doing here is that rather than impose our own concept of what the most natural vector space is for the text that describes an RFC to live in, we are allowing a machine learning model to come up with an ideal vector space that it wants to learn from. That embedding is going to capture all sorts of interesting things about the text, such as the punctuation of sentences or the use of mathematical symbols, etc. Second, we have a zero-shot protocol information extraction. That's where we're going to take the text that is now projected into the vector space of our technical language embedding, and we're going to automatically extract an intermediary representation, which I'll get into more later, which contains sufficiently much information for us to then, in a subsequent step, extract a finite state machine. So I want to stress this point that we don't do end-to-end in one step from English to FSM. We break it down into smaller subproblems. And we essentially create a structured intermediary representation, which is an XML document that has enough data for us to then, in a third step, extract the finite state machine in a rather heuristic manner. Finally, we do something useful with that FSM. In our case, it's attack synthesis. I'd like to stress that you can do other things if you care about other things. So if you were like, well, I don't care about attacks, I'm not a security person, but I care about bugs, I care about correctness monitors, whatever, well, boy, do I have other tools for you. There are other things you can do with these. But what we did was attack synthesis because, frankly, my dissertation is going to be about attack synthesis. So I applied attack synthesis. Let's talk about step one. In step one, we want to learn a technical language embedding. As I said, I don't want to impose my own personal moral, ethical beliefs about the natural vector space of RFC documents. Rather, I'm going to let the computer decide this. We use something called BERT. The idea of BERT, loosely speaking, is that it takes a contextualized approach to understanding what words mean. So the word reset could mean something different in different contexts because it is informed by the words around it. We train on roughly 9,000 documents and roughly 475 million words. So our BERT model is trained on quite a lot of data. That includes Stack Exchange, Stack Overflow, networking textbooks, all sorts of other things. Next, we want to do protocol information extraction. So just to remind you, in case you missed it, I now have some text that is projected into my vector space, and I want to translate it into an XML document. I'll show you what that looks like momentarily, which somehow captures enough data for me to then be able to extract a finite state machine in a straightforward manner. So I essentially want to read the text. So put differently, I want to teach a computer how to read and interpret the English language RFC document now that it has it in its own natural language, which is the BERT encoding. So here's a little snapshot from the DCCP RFC, and I'm going to show you how we would put this into a intermediary representation. First, we need to know what it means for the computer to read the document. So to do this, we invent a grammar shown here in Brockus-Nauer form. The grammar contains a few different types of tags. It has definition tags that are used to define states, events, etc. Reference tags that reference previously defined states, transition events, etc. State machine tags that tag essentially the structure of the finite state machine in the document, any references to transitions or other logic that relate to the state machine. And then finally, control flow tags that essentially capture logical structure in the FSM. So when you read these documents, a lot of times they have kind of complicated if-else structure. Often that's related to the indentation of different blocks of text. And our NLP is going to capture that using these control flow tags. So here's that same quote again, but this time it's now wrapped in our intermediary representation structure in our XML. We have a control block on the outside that scopes our search. We have a transition block that contains an entire state machine transition, including the source state and the target state. And then we have an event, and we know what exactly occurs on that event. So from the perspective of a formal methods person, I now have the source state, the target state, and the label on the transition in my Kripke structure. But from the perspective of a software engineer, I have an edge in the directed graph that is my finite state machine. In order to go from text to this intermediary representation without requiring a bunch of grad students to spend countless hours annotating things, we use a machine learning approach. In fact, we use two different machine learning approaches. We compare them. The first one is a linear conditional random fields model, which starts out by splitting text into chunks. It then extracts features from the embedding that the chunks are in, and then feeds those into a linear conditional random fields model, which builds on the Markovian assumption that the next state is predicated only on the previous one. We also experiment with a neural analog to this model, which is kind of morally the same, but it uses a neural network instead of the linear classifier. So we evaluate these against each other and also in contrast to a completely rule-based heuristic program, which we don't expect to do very well because this doesn't learn anything. The rule-based system, in fact, performs poorly as we expect, achieving below 35% token level accuracy and similarly bad span level accuracy. In contrast, the linear CRF and neural CRF models perform quite a bit better, with the neural one slightly outperforming the linear one. And you'll actually see in almost all the metrics we show today that the neural model slightly outperforms the linear model, which is another interesting result. So now that we've gone from text to embedding to intermediary representation, we now have these RFC documents that are expressed in XML like this. You can imagine big long document entirely structured with XML tags that say what's happening where. And now I need to extract a finite state machine from that. And I want to be very clear, this itself is not a finite state machine. A finite state machine would consist of things like this. actual transitions, right? I need to interpret the XML and extract the FSM. So how am I going to do that? Pretty much in the most boring possible way. I'm going to use an entirely heuristic algorithm that exploits the very structured nature of the XML to extract the FSM. Happy to talk about this more, but if you want to improve on our work, a good place to start would be on the Fsm extraction algorithm, because at the moment, we're not using machine learning for that step, and I think a fruitful thing to do would be to try that. Once we've extracted the FSM, we want to know how good is it, right? I mean, it's probably not exactly what was written in the text, so how close is it? So we compare against one that I wrote by hand. And to get back to the point about why all this is necessary, I will tell you it took quite a long time to write that by hand, because there are all sorts of subtleties when you get into a model checking environment of the ordering of events and the semantics of the channels that connect to processes that are not captured by just the diagram that you find in your average RFC document. So we expect to have 20 transitions in our TCP FSM. We also hand annotate or hand create an XML for the TCP RFC, and we call that our gold XML, and then our FSM from that is the gold FSM. So that one should have perfect annotations, and any bugs are related to either ambiguities in the text or problems with our extraction algorithm. So comparing these, we find that the gold FSM does quite well. We define a transition as being approximately correct if its source state, target state are both correct, and at least one of the events on the label is correct, but it might have like the wrong order of events, like say you maybe receive seen and then send ACK instead of the opposite or something. And in the case of gold, we find slightly fewer transitions than we expect to, but almost all the ones we get are approximately correct. With the linear neural models, there's quite a bit of noise. So although we find most of the transitions we expect to find, we also get a bunch of incorrect transitions. So comparing to our skyline, we find that another interesting result here is that in the very particular case of TCP, neural and linear models extract different intermediary representations, but actually all that is moduloed away by the finite state machine extraction algorithm. So any differences in the intermediary representations do not matter in this particular case in terms of the extracted FSM, although that doesn't generalize. Looking at DCCP, we find deceptively more transitions than we did with TCP, but we expect substantially more, so fractionally less are found. We expect to have 34 total transitions. With the gold, we only get 17. As you can see, the linear and neural models do not perform as well as gold, but again, neural slightly outperforms linear. Okay, so let's talk about kind of why we miss things, because as you just saw in these graphs, we missed a substantial number of transitions. So there's two problems. One is missing transitions. The other is incorrect transitions. And we'll start with missing transitions. Here's an example from the DCCP RFC for a transition going from close wait to last stack in which you send a fiend. This text contains mention of the message that was sent, the fiend, and the state that you started in, the close wait, but it does not mention the state that you go to, last stack. To find that, you would need to search, like, I think 4 paragraphs up in the document and find something indented back 3 lines, and it would implicitly tell you that it was last stack, but there's really no way that a computer could figure that out. And even a human being like myself reading this would have to search around for a while to try to figure it out. Also, if we wrote a rule to tell the computer to look that far back, it would cause problems when we parse other parts of the document. So this is a good example of why you can have missing transitions when you extract from an RFC. So we do an evaluation and try to figure out why it is that we miss transitions. And we do this by actually manually inspecting every single missing transition. We find that in the case of TCP, most of the missing transitions are due to omissions or ambiguities in the text. The thing I just showed you, I would consider to be an omission or ambiguity. I think it's ambiguous because you have to search in other parts of the document that are pretty far away, paragraphs away, to figure out where the transition is supposed to go. However, there's also a number of extraction errors for TCP. In contrast with DCCP, we also get some prediction errors, which is interesting. But that might just be a scaling aspect because there are so many more transitions in DCCP. So who knows? If you guys added like 20 more transitions to TCP, maybe I would get some prediction errors with DCP. I'm not really sure. It should be noted we miss very few for TCP. And additionally, this result with gold implies that the DCCP specification is substantially more ambiguous than the TCP one, because the fraction of missing transitions that are due to omissions or ambiguity is substantially larger than the fraction that's due to extraction errors, in contrast to the same analysis with the gold TCP Fsm, right? So in both these cases, we're using our skyline intermediary representation, so any problems are at the extraction level or in the spec. And again, the neural model is slightly better. Next, we look at incorrect transitions. So I've told you about missing transitions, and I've said that essentially they can happen for multiple reasons, but they mostly happen because of omissions or ambiguities in the text. Another question would be, what about when we make a mistake, when we extract a transition that's just completely off, it has the wrong start state or the wrong target state or both, or none of the correct events on the transition. In the case of TCP, they're primarily caused by prediction errors. So this would be something we can improve on, right? The prediction errors are part of our, and they're problems with our methodology. So our methodology can be improved to not have so many prediction errors, potentially even just by training on more RFCs, to be honest. In DCCP, however, looking at the gold, we find that a substantial number of incorrectly extracted transitions are due to omissions or ambiguities in the text. And so this, again, highlights that the DCCP RFC experimentally appears to be more ambiguous than the TCP one along numerous metrics that we can measure. We underperform on DCCP in terms of what how many transitions we can extract, and conversely, how many errors we have. And again, this suggests that DCCP is more complex. Okay, so now I've told you end-to-end that we have a way to automatically read an RFC document and extract a finite state machine. And I've shown you that the finite state machine has a number of errors, including missing transitions and also transitions that are wrong. And I'm going to claim, perhaps scandalously, that despite these errors, it is good enough to do something useful. To me, that useful thing is going to be attack synthesis. So that means the automatic generation of attacks against the protocol. But you could also view this as the automatic discovery of potential bugs. So I used an attack synthesis tool called Cfrg, which I created, which is why I used it. I presented Cfrg at SafeComp 2020, which was in Lisbon, Portugal, but I was over the internet because of COVID, unfortunately. So hopefully next time I'll get to go to Lisbon. Cfrg takes as input an extracted finite state machine like the one we just generated. A linear temporal logic property. This is just a formalization of what it means for the state machine to be correct. So an example of a property would be that there's no active close in DCCP. So I could have a property saying you never have both peers closing at once. It then creates a system in which two peers are communicating over a vulnerable channel. So it injects a vulnerability into the channel between them, a man in the middle, and it asks if in that threat model, the property could be violated. So we're not asking if the protocol is correct on its own. We kind of assume it is. In fact, we don't even look at properties unless they're satisfied by the model in isolation. But we want to know, under attack, is this still satisfied? The spin model checker reduces this to a language emptiness problem by intersection of a Buki automaton with the system. But basically, it does fancy formal methods from the 80s. And it says, no, the system is not correct when it's under attack. Here's a counterexample, which is just a sequence of events that the system goes through in which the property is violated. Finally, Cfrg takes that counterexample and turns it into an attacker program that simply replays that attack. So it's a pretty simple approach. We looked at two case studies, TCP and DCCP. The FSMs shown here are made by me and have been extensively model checked with a number of properties and shown to satisfy all of them. So these can be viewed as perhaps more canonical than the FSMs that you'll find in the RFC documents or in any number of security papers where they do maybe graph-guided search, but they don't really care that they satisfy formal mathematical properties. For TCP, we use 4 properties. The first 3 came from my paper when I presented the Cfrg tool, where I also used TCP as a case study. And the 4th was written by Ben Weintraub. All 4, though, are written based off a close reading of the TCP RFC. Likewise, we also have 4 properties for DCCP. I don't think these are incredibly interesting properties, so I'll kind of skip them, but I'm happy to talk about them afterward if people have questions. We generate a number of attacks This is kind of a confusing table, so I'm going to try to break it down into subpoints. Essentially, with TCP, there's only one property with which we are successfully able to generate attacks using any of our extracted finite state machines. We generate very few attacks with TCP, but all of the attacks work, meaning all of them are confirmed on my handwritten model. So there's no false positives. In contrast with DCCP, we're able to generate attacks using all four properties. However, we get some false positives. So for example, with the third property I wrote for DCCP, using the Fsm that was extracted with our linear conditional random fields model, we generate 13 attacks and all 13 are false positives. So again, there's sort of a noise to signal ratio thing here where I'm generating more attacks with DCCP, but there's more errors. I generate very few with TCP, but there's 0 errors. Again, to me, this seems to indicate more ambiguity or more complexity in the DCCP RFC because errors in the attack synthesis step are caused by errors in the finite state machine. So this is fairly predictable from the results I showed you up until this point. Okay, when I say the word attack, it can mean any number of things, and people use this word rather liberally. So I want to give some examples of what I mean by an attack so that you know what exactly I'm saying. One attack would be to inject an ACK to the first peer in a TCP active passive establishment routine in order to, if I remember correctly, get that peer stuck in scene received because it can non-deterministically decide to exit. But if it doesn't decide to exit, for example, if it's configured to have a very long timeout time, then it could stay there forever, or essentially forever. They may sound a little silly, but if you talk to Samuel Giro at Lincoln Labs, he'll tell you that he's found TCP implementations in the wild that have this bug. And in fact, I've found Stack Exchange queries, even experts exchange queries from people who had this problem where their TCP connections hung forever because they'd configured the timeout incorrectly. Another example, which is much more complicated, which we also find, would be to elaborately spoof each peer in a DCCP connection in order to guide the other one into close rec. This is sort of a silly attack because I'm not really sure what like an elite Russian hacker would want with this. However, it is a violation of a correctness property because there's no active-active close in DCCP. So if I can induce an active-active close, maybe I can cause a deadlock or something. And I want to point out this interesting point that because our approach is based on model checking, we'll find many, many variants on kind of the same attack. And so indeed, we find many variants on this attack. And I can show you dozens of different ways that essentially do the same thing. I want to conclude with future directions. So the research I showed you today was presented at S&P to a security audience. And you know, there's kind of a certain set of things that interest them in terms of breaking protocols. But I think for you, you may have different interests in terms of maybe building protocols that won't be broken from the first place. So it would be nice if we could automatically highlight omissions and ambiguities in the RFC text. And I think that we're part of the way there. If we can kind of take our tool and make it say, I'm kind of confused about how to interpret this piece of text, could you clarify it? That might be a useful functionality for RFC authors to be able to know when something they wrote is not entirely clear. Another thing I'd like to do is automatically suggest bug fixes. So if I extract a finite state machine and the RFC author looks at it and says, yeah, actually that looks correct. I think that's what I intended to describe. And then I find an attack against it. Well, it'd be nice if I could use some synthesis techniques from the formal methods community to automatically suggest a patch that would resolve that problem. And we actually have an undergrad working on that problem with us right now, which is very exciting. A completely different kind of vein of research that we'd like to undergo is to extract logical properties. Right now, I'm writing those properties from hand. That's not easy. Writing properties from hand is maybe not quite as hard as writing models by hand, but they're both much more difficult than they seem. And it's very easy to write a property that, for example, is vacuously true, and then you really can't do anything with it. So there's a lot of logical subtleties in these things. We'd like to offer support for secure protocols. There's a lot of kind of interesting problems to this, like capturing the arithmetic that goes into the cryptography in such a protocol, capturing secrecy requirements, and we might have to take a different approach in terms of the backend. For example, maybe relying on Proverif or Tamarin instead of Quark. I think that finally, it would be really nice if we could take all of these different ideas and turn them into some sort of cohesive software suite for an RFC author in the loop. So when an RFC author or authors are writing an RFC, it would be nice if they could run our code and be told, hey, this seems ambiguous. Maybe you could clarify this, and they could kind of have a feedback loop to do so until they automatically get an unambiguous piece of text. And you could even imagine perhaps mixing formal language with the English to make it so that if the RFC author actually likes the way they describe something in English, they could just give little formal hints about how to change it. And that's it. With that, I'll take any questions. Thank you very much.
Okay.
All right, thank you very much. Excellent talk. I see a couple of people in the queue. Who's first? Yoshifumi Nishida, I think I see first in the queue.
My name is Yoshi Nishida from Amazon Web Service. So I think this is very interesting research. Thank you so much. And then this might be a part of future direction, but one of the complicated things for TCP is congestion control and the loss recovery.
Yeah.
And then I'm wondering if we, you can apply this technology to the congestion control or loss recovery and how it's promising. That's what I'm curious about it.
Yeah, that's a fantastic question. My current project is congestion control. However, I have not been applying NLP to the problem. I've been manually modeling a congestion control algorithm of interest. I think that congestion control is pretty complicated, and it would be fantastic if we could partially automate the modeling. But I'm trying to get an intuition for the modeling to begin with by doing it by hand before we consider automating it. But I mean, you basically predicted the next year of my life. So yeah, that's what I'm doing.
Thanks so much.
Thank you.
All right, thank you. Michael.
You said you use, you analyze the text to get the finite state machines. Most of the transport RFCs contain a graphical representation of the finite state machine. So did you also consider using that, or is that too hard or too weak? Or
that's a great question. So I did write a little toy script that could read the ASCII diagrams in RFCs and got it to work on quite a few of them, but there was nothing very scientific about it. I just kind of wrote a little heuristic Python script. I've spoken to Maria about this, and apparently Maria did the natural language processing for the most part on this project. I did all the FM. Maria says that there is kind of a field of NLP that deals specifically with diagrams and figures, and it could be applied to this type of problem, which is an interesting approach. I will tell you, however, that the FSM diagrams are missing a bunch of information. For example, if I recall correctly, I think that the TCP FSM diagram is missing a core component of the active-active close routine. And in the DCCP one, I think that there was, again, oh, you know what? I think in DCCP, there's a transition that's shown in the diagram, but not in the text. There's a bunch of places where the diagrams are missing things. There's also this problem when protocols have multiple diagrams that have to be somehow merged. Like if you look at LTP, which is a pretty interesting protocol that's used in space exploration, it has, I think, like 7 or 8 FSM diagrams in it that all interact in I would say mathematically ambiguous ways. Even DCCP has multiple FSM diagrams because it has one for the state changing, stable, and unstable, and then another one for the communication. So diagrams are interesting. I'm not personally working on that problem. I do think it merits attention, but I don't think it's a golden ticket to automatically getting good FSMs from RFC documents.
no, but it would be very good. But it would be very good. So if there is a disagreement between your FSM representation and the one shown on the graphic, to make that available, to make this difference available to the authors, because that might not be intended.
Yeah, that's a good point. We mention these things in our paper, but I'd also be happy to summarize some of the differences in an email to whoever would find that interesting. So maybe offline you can help me know who would like to know about things I found in the RFC that maybe could be improved.
Thank you.
Thank you.
Hi, Tommaso Pecorella, University of Florence. Great work, very interesting. I want just 2 questions, quick. The first one, you've shown 2 different methods, one with linear, one with, I don't remember, sorry. Anyway, I wanted to ask if they are wrong in the same way, or they actually could be used together to cross-validate each other and say, okay.
Yeah, that's a good question. I haven't thought about that. Maria probably has. Yeah, I'm sure that you could use them to, you could do some sort of intersectional approach potentially, right? Where you have like a higher layer that takes as input both models and then finds kind of where they agree. That sounds interesting. I haven't tried that, but I think it's a good idea.
Thank you. And the second one is if you are taking also into account, not now, maybe in the future, the problem of the length of the fields, because sometimes the state transition is actually governed by some fields that might be either too short or too long, or, well, usually too short. And also that might be a problem for the state machine.
Yeah, that's a great question. I would say that prior work before I started my PhD by my group, specifically by Samuel Giro, who, as I said, is at Lincoln Labs now, working with Maria, applied similar techniques to figure out the packet structures of protocols using natural language processing applied to RFCs. And you could potentially combine these approaches, right? So if you have one approach to find the packet structure and another to find the finite state machine, and then you can go from just reasoning about kind of your atomic propositions of like seen and feen to actual full-fledged packets, then that sets you up to pretty nicely be able to make arithmetic statements about the contents of those packets, right, such as their length. So that would be a next step. However, from a formal methods perspective, it's complicated because you get into a state space explosion problem. So you probably wouldn't want to use model checking at that point. If you're going to reason about the packet details, you'd want to use another approach. But yeah, it is interesting and something we've thought about.
Yeah, thank you.
Thank you.
Great work.
This is Antoine Delignat from Microsoft. So I think there was one thing that I found a bit missing in the evaluation. So obviously your current extraction don't have very good accuracy. And also you have the additional loss from the translation to state machine. So have you tried to actually do the work that you suggest in the future steps for the for instance, for TCP or for DCCP? Which would be essentially measuring how many changes you need to actually make in the original RFC until you get to the point where you actually don't have any missing transition anymore and you don't have any false transitions anymore. Because it feels like with that many errors, you would need to essentially completely rewrite everything, or it would be like very frustrating for the RFC authors to actually do that methodology. So do you have any kind of thought on that, or did you do any experiments on that?
Great question. I have two thoughts on that. First of all, we have not worked on this yet because I think there's a lot to improve in our methodology before we try to improve the RFCs. So, I mean, just from an academic perspective, I understand that as like the IETF community, you are more interested in improving the RFCs, but as academics working on trying to find cool ways to extract information from documents, we're perhaps focused right now on improving our ways of extracting information from documents. And as you can see, with prediction error, there's a lot that we could improve on, right, by training on more documents and improving our model structure. That being said, I think actually that what we'll eventually find when we do get to doing this experiment is that the amount of changes necessary is not that great. I think for the most part, it would be things like you have a sentence in which the target state is implicit, and you just add the words to seen received to the end of the sentence, and now it's explicit, right? Essentially taking things that to a human are implied and making them explicit, because I'd rather have a slightly redundant, boring spec that's unambiguous than one that's very cleverly written and I get confused by. So I actually do not think it would take that many changes in order to make it unambiguous.
Okay, thanks.
Thank you.
All right, thank you. A reminder that we're using the Meetecker queue so we can do the local and remote people in the queue. Last question, I think, is by Jonathan.
Yeah, can you hear me?
Yeah. Yes.
Yeah.
So I spend a lot of my time doing tamarin modeling. So this is something I think a lot about. I'm interested to know why you're using FSMs, because almost all protocols that I've come across cannot be expressed as an FSM. You need tokens, or they have states, or you're actually very limited to maybe just TCP. I can't imagine what other ones don't have state.
Yeah, this is a fantastic question. So people who work in Tamarin or Proverif or dare I say Cryptol are interacting with mostly cryptographic protocols or protocols that use cryptographic primitives, and they care about things like secrecy and privacy, and I care about those things too. But because they care about those things, they need to reason about threat models where secrecy or privacy or confidentiality, et cetera, could be violated, and attacks against those things. And FSMs are, I would say, probably not the right approach for that. So I think we agree on that front. And I think that maybe a more type theoretic approach like what Tamarin does is quite good. There actually are quite a few protocols that have at least components that can be studied using FSMs, mostly communication protocols. Examples include LTP, TCP, DCCP, SCTP, SFTP, FTP, and some also some newer protocols I've been looking at that are not related to IETF, which we'll release in future work. So I would say that many things that are communication protocols that have handshakes in which you establish some sort of connection are very well described by FSMs. But another aspect to your question is that we often will take a protocol and break it into chunks and say this chunk can be studied by model checking with an FSM representing that component of the protocol, but this other chunk might be best studied in some other way. So the cryptographic aspects are probably not suitable to model checking. Yeah, thanks for the question though, great question.
All right, thank you. Really excellent talk, really excellent questions. There's a bunch of discussion in the chat as well, which you might want to look at in a couple of minutes. So thank you again, Max, for your talk.
Thank you very much.
Thank you very much. All right, thank you. So our next speaker today is Jane Yen from the University of Southern California, who is going to talk about tools for disambiguating RFCs.
Yes, thank you.
Okay.
Okay. Can everyone hear me? Okay, great. So hi everyone. So today I want to talk about our work that I worked with my advisors, Barak Raghavan and Ramesh Govindan. The topic is tools for disambiguating RFC. Let me start from giving you some numbers that I got from the RFC editor website. Here, this table shows the number of published RFCs each year from 2016 to 2021. We can notice that the published number ranges from almost 200 to 300. So assuming each RFC is about 10 pages, that means there are about 2,000 or 3,000 of pages every year that should be reviewed and studied and considered. It doesn't sound like a small number to me. It also indicates that great human efforts involved. So human effort is involved in various parts of the specification production process. And as an example, here is a working group. They will need to gather and discuss which and or what protocol needs to be standardized, and there will be one or more specification authors composing the contents of spec. Although it might be obvious, the content is full of domain-specific knowledge and would require professionals to verify the content. Any unclear detail is picked out by human examination. When we speak of the concerns about the quality of a spec, it is hard to neglect the impact of ambiguities. With the existence of ambiguities in a spec, different protocol implementers could interpret the content differently and generate multiple versions of the protocols. And here's one example which might cause different interpretations. It says the checksum is the 16-bit ones complement of the ones complement sum of the ICMP message starting with the ICMP type. At first glance, it might not be obvious why the sentence is ambiguous. However, when we focus on the last part of this sentence, it explicitly mentions the checksum starts with ICMP type, but it doesn't mention where the checksum computation should end. So how could this affect a person's interpretation? Here I show the ICMP header to help illustrate how we can at least come up with two different interpretations. One is to checksum only the ICMP header part, and the other is to checksum both the header and the payload. As shown, the two different interpretations would lead to different protocol implementations. So with this example, we noticed that using an ambiguous specification could not only result in different implementation, but also result in buggy implementations and or security vulnerabilities. So if we go back to our scenario of generating a spec, the working group and the spec authors all know the importance of delivering correct message over the spec to spec readers. So there are some guidelines to follow, and they are useful to reduce the ambiguities. But do we know whether we are close to near zero ambiguity for the specification? Motivated by this question, we presented our work in last year's SICON and ANRW. Following, I will introduce what they are about respectively. The first one is SAGE. In this work, we get to know what ambiguity exists in a number of long-standing protocols. Specifically, we uncover 5 instances of ambiguity and 6 instances of underspecification in ICMP Rfc. With an ambiguous specification, we are able to generate executable code that can interoperate with the third-party code. And SAGE generalized to significant sections of BFD, IGMP, and NTP. Well, as an introduction, I leave some detail in our paper and aim to give an overview of it. So in SAGE, we apply natural language processing techniques on it to discover existence of ambiguities. To do so, we need to understand the semantics of a specification, which is commonly termed as the semantic parsing. And ultimately, we want to leverage the results from semantic parsing to generate low-level executable protocol code. Since semantic parsing is not perfect and may possibly never be perfect in the future, once ambiguous sentences are found, we will need to involve human efforts to edit those sentences. When a specification is unambiguous, executable protocol code can be automatically generated. And in this work, we face a number of challenges. First, semantic parser only parses generic terms, but specifications could use domain-specific language such as checksum, once complement, etc. And second, semantic parsing is not perfect, and therefore multiple representations might be generated, but only a subset is valid. Finally, when we generate semantic representations, we need to convert them into correct the executable code. In this work, we make the following corresponding contributions. First, we extend the generic semantic parser with domain-specific syntax and semantics. Second, we automate disambiguation of poor semantic representations with defined checking rules. And third, we compile semantic representations into executable code. SAGE has 3 components that correspond to the contributions, and respectively, they are semantic parsing, disambiguation, and code generator components. A complete Rfc parsing workflow will look like this. In addition to the already introduced 3 components, human will be involved in the loop. After the disambiguation phase, if more than one representation remains, it means we discover ambiguities, so we provide feedback to the user, who is likely the specification author, to resolve ambiguity by rewriting the sentences. Also, if a sentence is unambiguous, SAGE will proceed to map the intermediate representation to a code snippet. The code snippet will undergo unit tests to check if it performs any underspecified protocol behavior. I will introduce the main idea of each component. First, semantic parsing component. The purpose of doing semantic parsing is to derive a semantic representation. Therefore, what we can expect is to taking a textual sentence and turn it into a chosen intermediate representation. And in our work, we use a semantic representation called a logical form. A simple logical form is composed of a predicate with a number of arguments. The key observation here is that a logical form is a unifying abstraction for disambiguation and code generation. We do not change the functionality of the parser itself, but for it to properly parse our text, we have to extend the syntax and semantic parts. For example, the NLP parser wouldn't recognize all the nouns or noun phrases. So we have to use, in this work, we use a generic parser called SpaCy, and we extend the Spacy's term dictionary with networking terms such as one's complement. And for the semantic parts, specification might include some idiomatic usage. For example, the equivalent mark in 0 equals to echo reply is not a sign that can be processed by the generic parser. After we add the semantics for it, the parser could understand that it is an association relations in the sentence. Next, let me introduce how we leverage logical forms to discover ambiguities. If the NLP parsing yields something other than exactly one logical form, we call it a true ambiguity. An example of a zero logical form case is that a sentence is incomplete due to a missing subject in the sentence. And another example of more than one logical form case is that a sentence uses imprecise language, such as using a terminology that can be interpreted as two different concepts. So the NLP parser has limitation and could generate additional logical forms that do not indicate the true ambiguity cases. Therefore, we define 5 different types of check-in rules to eliminate these additional logical forms. The 5 check-in rules are type, argument ordering, predicate ordering, distributivity, and associativity, respectively. But for more detailed introduction of these 5 check-in rules, you can find in our paper. So after disambiguation, every sentence uses only one logical form as an unambiguous specification. Then we move on to the code generator. The code generator works as follows. It checks in a logical form and its contextual information and turns it into executable code. This example is simple and straightforward to map a logical form to an executable code, but this converting process can get far more complex than this example. We also include more complex example in the paper, so you may check it out later. I'm only giving you an idea of what kind of evaluation we've done in SAGE. We put the SAGE is on ICMP RFC. We apply the SAGE on our ICMP RFC and use generic Linux ping and trace route on the sender side, and use the packet formulation function to generate a reply packet back to the sender. The tested ping and trace route programs are able to process our automatically generated reply packets. As for showing the efficacy of applying disambiguation rules, we analyze how many logical forms are generated as the base and how the value goes down to 1 after all checks are complete. I have focused on how we use SAGE to understand an RFC. But in our ANRW paper, we extend the discussion to cover what else challenges haven't been addressed and how the work can be possibly extended. While Sage takes a significant step towards automatic specification processing, there much work remains. In an RFC, there are many components. Sage is able to parse packet formats, pseudocode, but there remains other components Sage hasn't supported, such as state-machine, communication pattern, and architecture. In addition to the limitations shown, there are other challenges that can also be considered from code generation perspectives. Thinking of Sage as not only a method to understand the level of ambiguities, but also a method to automate the code generation. There is a lot of room to automate the code generation part. For example, Sage mostly parses sentence by sentence to determine a sentence ambiguity and generates code according to the order of descriptions. However, it's unrealistic to assume that all specifications use self-contained sentences every time. That means we should consider the relationship between sentences and how a sentence can provide the context to generate the code for another sentence. Another challenge could be discovering the mismatched or miscaptured behavior. For example, we have both text and syntactical components, which might be a diagram. What if the information in the diagram is not consistent with the textual description? Or what if a piece of information is illustrated in a diagram, but there is no textual explanation? Should the protocol implementer implement that part of the diagram? Supposing that we are able to process a single RFC already, what about some protocol describing its functionalities or constraints across multiple RFCs? In some cases, a protocol gets revised and added more constraints in implementation with the publication of another RFC. How to aggregate the information from multiple RFCs? And there's another type of challenge, which is aggregating the information of multiple protocols instead of one protocol. In practice, we send packets with a stack of protocols. When we want to generate the code of a stack of protocols, how do we exactly correctly organize and categorize the information from diverse RFCs? In addition, how do we select the constraints or values while the stack of protocols is slightly different? Yet another interesting perspective is to consider the logical functionality versus the performance of a protocol implementation. A protocol RFC usually focuses on describing its logical functionality and leaves the flexibility of implementing code to any reader of the RFC. That means we will know the protocol implementation should be logically correct, but not about how the performance will be. If the spec author suggests any performance-oriented implementation, will we be able to differentiate them and leave out the implementation as the flexibility or the freedom of the code implementer? The last part I would like to present is our current work direction. I have shown this figure previously. It illustrates how we process an RFC document and involve a feedback loop to indicate the human user where the ambiguity exists. I would like to point out there is still room to improve the involved human efforts, such as how to assist editing ambiguous sentences or to extend Sage to support more protocols. This leads to another two challenges we need to deal with. Considering how we can assist editing ambiguous sentences, we might also want to ask, can we avoid writing an ambiguous sentence in the first place? As for the other challenge, we have only talked about a subset of specification components. What else protocols are we going to support? Regarding the first challenge, we are motivated to design a user interface tool that can guide the spec author to input only essential information for the protocol. Then we will use the extracted essential information to produce unambiguous readable English text and executable code. As for the second challenge, we are aware that stateful protocols require considerably more complicated operations, and many protocols belong to this group. Unlike stateless protocols, a stateful protocol is required to keep internal states to interpret packet contents given the current state. The ability to keep historical information could allow us to significantly hover more protocols. So now let me piece together. We would like to give the user a friendly interface that is able to extract the essential information we need without ambiguity. As one of the options, we might design interfaces similar to Microsoft Arcade, which leverage the web interface and puzzle-like shapes to generate executable code. But for us, our output becomes the English sentences. Once we design a parser and parse the information received from the user interface, we leverage the information to both compose easy-to-read English sentences and the executable code. The last part we would like to fill in is what essential protocol elements are considered. As I mentioned, we want to deal with stateful protocol from our internal discussion. We believe a reasonable set should contains schema, last received packet, output packet, and the program states. This constitutes our vision of a useful tool to generate bidirectional, unambiguous English text and precise executable code. This is my last slide. I'm happy to take questions and also interested in learning your opinions about the current work. I leave my contact information and the open source code of the mentioned Siege on the slide.
All right, thank you, Jane. A really excellent talk. Does anybody have any comments or questions about this talk? A couple of minutes to come up, maybe. I think one of the things which interested me about the work is that it really nicely complements the previous talk, and that we have you're modeling aspects of the protocol which are not perhaps captured by the finite state machines, and so there's a nice complement between the two. Well, one question for me. I mean, both this mechanism and the mechanisms you've developed and the mechanisms in the previous talk are all based around natural language processing and so on. How expensive are they to run? What's the sort of runtime for these models?
The runtime isn't long. For processing the ICMP RFC. It contains 7, or sorry, I forgot the exact number, messages, but to process that whole RFC runs for about 5 minutes.
Okay, so it's not instantaneous, but it's not crazy long. Yeah. Okay.
Yes.
Good.
Because
yeah, okay.
Part of the complexity is due to the NLP parser, that it has to analyze how many different kinds of way to generate the semantic representation. So there are ones that you have so for example, if you have a noun phrase that can be interpreted in multiple ways, then all of them have to get enumerated to generate the representation. So that takes the majority of the time.
Yeah, okay, makes sense. All right, thank you. Rutger Falk, I guess you're in the room.
Yes, I am. Thanks. Well, okay, maybe I'm a little bit sidetracking with a comment to start towards Colin. Colin, you said, well, okay, we are used to do the specifications in English prose. well, okay, kind of sometimes we enhance the specifications by some formal stuff. I would not consider ASCII art as real formal enhancements of the RFCs, but they are in there and in the ICMP RFCs, obviously. And kind of, I wonder, how does the NLP actually deal with stuff like that? Are you kind of doing the manual transformation to reasonable data structure definitions by hand, and continue from there, or the other way or asked around, would it actually help you to have in the RFCs more formal and more modern ways of specifications of the relevant data structures?
Okay, so for the ASCII art part, we didn't use the NLP NLP tool to parse that. Instead, we parse the ASCII art of the packet header by writing another small program to parse it, and it can automatically extract the structure, the packet header structure. So that's one of it. And I just want to address in another perspective is, as our current work is trying to extract the essential information out of it, by looking at those essential information, we are thinking not only to generate the English text or the executable code, we are also thinking to use those information to generate the diagram automatically, so that in the future we expect that the authors can directly compare the diagram or can automatically use the diagram generated in the RFC so that it can help illustrate the idea. So I hope that answered your question.
Yeah, great, thank you. Jonathan Hyland, I guess.
Hi, that was a really interesting talk, thank you. I was just sitting there thinking, wouldn't it be easier for us to formally specify protocols and then use some tool with NLP to generate the prose spec? And then we can be sure that the prose spec actually implements the formal specification, and then we can check the formal specification.
Yeah, so I agree that is also one way to do that. The thing is, we have to fill in the gap of how to convert between the formal specification of formal language, formal specification language to the English text. So that part is still missing over there, and I think there's one problem over here is there are too many different kinds of intermediate representation. So formal specification language is sort of like another intermediate representation. You can always choose like different ones and then try to fill in the gap from the English text to that representation. So I would say that is totally doable and actually a good way to go from it. But our first work stage is to just directly choose a simpler way to do the first step to analyze whether we can find some ambiguities. But for further specification, I agree that writing a formal specification language and then generate the English text might be also a very doable way. But I think we start from like a smaller scope from the state machine to just have some like simpler, simpler language, English text language, and just to generate a very cool, simple English text. But we have to see whether that is a good approach first. Otherwise, that we are not sure whether we should go from the formal specification language to the English text, because formal specification language text I believe it's more, you need to take some time to learn it, to pick up, and then to do those things. But if we just extract the essential information, like just some key value pairs, and we can just directly go from those information and then generate text, that might be also another good way to go. Yeah. Thank you.
Great, thank you. I'm conscious that we have one more talk and we're running a little behind time. So again, thank you again, Jane. I think that was a really excellent talk.
Thank you.
All right, thank you. The next speaker is Chris Wood, who I believe is there in person. Is that right?
Yeah, hello. Trying to figure out how to control this remotely.
I, in theory, have passed you control.
Great, I got it.
All right, so over to you, Chris.
All right, thanks. All right, everyone. My name is Chris Wood. Do some work at a number of places in the IETF, in particular in the Cfrg as of I guess recently. I help out producing technical specifications for that particular group. And what I'm going to try to talk to you about is, I think, a problem that has been emerging in that particular group, which is it's not only in the Cfrg, it exists elsewhere. And it's on this topic of, how can we improve the quality of specifications in the Cfrg and elsewhere in the IETF and IRTF. I should say, first and foremost, that this is very much based on my own personal experience writing these things, trying to communicate technical things in a way that's clear and concise to people. I have not talked about this with many other people. I've not asked for a review on the slides. So if you disagree, that's cool. We should talk about it. This is not consensus of the Cfrg in any way particular, or any way, shape, or form. Also, I'm not trying to point fingers or blame people. In fact, I work on a lot of documents, so I should just be pointing the fingers at myself. I really want to see if there's a reasonable way forward for the IETF and the IRTF to improve the overall quality of the outputs. And so this is an attempt to do that. Okay, so I'm going to start with what I think is sort of the problem, or maybe it's not a problem, but depending on your perspective, but I'm going to refer to it as a problem. So in theory, the Cfrg is chartered to do a lot of things. It's pretty broad charter. You could summarize it in the sentence that I have sort of quoted here. It's meant to sort of effectively bridge things that happen in academia, in theory, and sort of bring them into practice. Documenting things that are written down in cryptographic related papers or published in conferences and whatnot, and present them in a way that people can actually use them. And to do so via what are referred to as informational RFCs. An informational RFC just contains information. It does not go through the same sort of editorial or rather review process, the same sort of rigor that other things in the IETF and elsewhere go through. So the sort of bar to publication of an informational RFC has historically been lower than that of a standard track or proposed standard. That's kind of a problem because in practice, the Cfrg specifications, I think, demand a much higher bar for what they're actually being used for. You could go back and look at many of the specifications or RFCs that came from the Cfrg, and look at how often they're used and referenced in practice. And it should be very clear that these are very, very important documents, things like HMAC, HKDF, CUR209, EDDSA, and HPKE. That's a recent one. These are all fundamental to how the IETF and even other IRTF groups design, reason about, and build protocols, the security protocols in particular. Moreover, these specifications that are developed have a huge audience. They are meant to be useful to people who are designing protocols. They want to be able to consume these cryptographic objects. They're also useful to people reviewing these particular specifications to make sure they are consistent with things that have been like analyzed, improved in practice. And there's probably lots of other audiences as well. But the gist is that the stakes are very high, I think, for the things that the Cfrg does, despite what the charter lists. So quality of its outputs is critical. So I'm going to be trying to focus on like specification quality here. What do I mean by specification quality? So I claim that there are at least three sort of fundamental aspects of a technical specification. First of which is like the functional piece of it. Like, what does this thing do? And Cfrg is actually kind of, it's quite nice in that like typically the things that it works on are much, much simpler compared to protocols that the IETF standardizes. So it was only until I guess recently that we actually started looking at real protocols that involve like sending messages between different parties. Historically, it's just been like, an algorithm, specify an algorithm that has some steps and an API and a syntax and stuff like that. So I'm just going to refer to these things as objects. And the functional description of this object is, what does it do? What's purpose? What is its purpose? Like, I just kind of want to reason about how I might use and hold this particular thing. The second part, or a second part, is what I refer to as the syntax specification. That is like, what does its API look like? How would I interact with it? If I were to implement this in like a type-safe language, what would that API look like and how might I enforce it? And the third component is like the actual implementation. Like, how would I write code to implement this particular algorithm and to do so correctly? And keeping in mind the different audiences that were listed earlier, it's important to make sure that each of these different components of a specification are tailored to the relevant audiences. So for example, the implementation specifications should be written such that implementers can actually use it and implement the thing correctly. Whereas like the functional piece of a particular specification needs to be written such that people who want to just figure out what this thing is doing can do so without having to understand the implementation details. Like, you shouldn't have to be a cryptographer to understand like what an RSA signature is or whatever. Like these are like simple concepts, and people building these protocols in the IETF should not have to be experts to use them. They should be like easy to use, hard to misuse, that sort of thing, blah, blah, blah. Okay. And to figure out whether or not, the specification or the different components of a specification written satisfy these goals, there's questions you can ask yourself as an editor or an author of a document. I think the first and foremost one that comes to mind for me is like, is the specification easy to use, easy to understand and use? Like, can I just like read it and figure out what the thing is doing? Can I reason about like the behavior of the cryptographic object? Could I reasonably like think about what the API might look like and what the exceptional cases might be if I try to hold this thing the wrong way? Second most important question is like, if I'm reading this thing and I were to try to do a faithful implementation of it, would I produce a consistent and correct implementation that I could interoperate with other people's implementations? And that depends on the behavior being well defined. It depends on the implementation description being clear and so on. And lots of other questions I'm sure would come up to try to figure out whether or not you're on the right track. So I want to look at a couple examples that the Cfrg has done and to try to reason about these two high-level questions. Is the specification easy to use and understand? And will it yield consistent and correct implementations? And I picked on an RFC that gets picked on a lot, RFC 8032 for ETDSA. It has this one component of the draft specifies how you like verify digital signatures. Don't need to read this. In fact, I encourage you not to read it because you might get bored. But I will just note that in this final piece of this particular body of text, they have something like, you could do, or we recommend you do this one thing for correctness and security and safety, but maybe if you're feeling up for it, maybe you do this other thing instead. And it turns out that has been the cause of tremendous amount of pain in practice. It's been the cause of like security problems in practice. People just don't agree on like what signatures are valid, and that's probably not a desirable property for a digital signature scheme. So I would claim that to answer the first question, like, yeah, the specification is easy to use and understand. Like, it's actually a really well-written technical specification. But was it written in such a way that it yields consistent and correct implementations? Unfortunately not. Just my own personal opinion. Like I said, if you disagree with any of this, that's fine. We could talk about it. Okay, another example is actually an ongoing specification that's being developed right now. This thing called opaque. Opaque is without describing what these terms are, it's basically it's a compiler for taking a bunch of different pieces or a bunch of different cryptographic algorithms, gluing them together, and the result is a password authenticated key exchange protocol. Conceptually, like once you, if you understand the object and understand the protocol, it's pretty easy to think about. Unfortunately, to like actually understand the spec and implement it correctly, you have to understand and be familiar with all these other concepts, like what the authenticated key exchange thing is, what this VOPRF thing is, what hash to curve means, what a prime order group means, and there's other relevant specifications not listed here that are likely also in this dependency tree that are like necessary to understand opaque. So to I guess answer the two questions, I would say that this specification is not easy to understand and use. And will it yield correct and consistent implementations? There's test vectors and people have done it. So maybe that check is a bit biased, but maybe there should not be a check there because it's still an ongoing draft. So we don't know. But the takeaway is that like this is an incredibly complicated document. It could be potentially be much simpler if you try to change up like what the features that were supported are and whatnot. But it's not simple to understand, and that's not great for security relevant protocols. Okay. So I think the core problem here is that the nature of the work that the Cfrg does is highly technical. And it's highly technical and it has to be consumable by like different audiences with different levels of expertise and different purposes for consuming that technical specification. Like an implementer just wants to know how to implement the thing, the protocol designer wants to know how to use the thing. And the problem is like this is a hard problem. So there's like no way around it other than just acknowledging that this is a hard problem, like writing a technical specification that ticks all of these boxes in such a way that it's maximally useful, easy to implement and correct and consistent is not an easy thing to do. And we've been trying to do it for many, many years. I do think we're improving, but I think there's more that can be done. I'm trying to shine a light on, potentially more things that can be done. So I want to call out one particular draft that is going through the process right now to kind of showcase how we chose to structure the specification in such a way that it does try to tick some of these boxes in what I consider to be a useful way for people who are consuming the spec. So this draft called hash to curve, it is, again, without going into any of the math details, it's basically just like a hash function, or it's a specification that describes a hash function that takes as input arbitrary data, a string, and produces a point on a curve. That's basically it. At the highest of levels, it's a very simple interface. It can be summarized in this one picture here. Its internal steps are like quite simple and pretty easy to, I guess, like if you don't want to know more, it's easy to figure out, I guess, what the, I guess, high level functionality is basically from this. So as I go through the next couple slides, just I guess keep in mind and ask yourself, you know, is, like, based on the limited set of information I'm going to present, like, is this specification easy to use and understand, and will it yield consistent and correct implementations? Okay, so let's consider the functional description of this particular specification first. That is, what the part of the specification that's written for the people who just want to understand what hashing to curve means. So if I'm reading this specification for the first time, I might go to the part of the spec that describes like what this functionality is, and I come across this blurb here that describes hash to curve with some input produces an output, and there's these few steps here. Okay, but maybe I want to know like what these steps are. Helpfully, there's like similarly simple descriptions in the draft that describe each of these different steps without any of the implementation details. Like, you don't need to understand them to figure out like what this particular function is doing. Like this is sufficient, I would claim, for understanding what like the function of hash to curve is doing. And I think that's like a good balance for this particular audience. Now let's consider the API designer. So an API designer looks at the same, you know, section of text. It sees like, oh, there's this thing called map to curve as one of the steps that I have to, you know, invoke when like in an implementation of hash to curve. What does this map to curve thing do? There's specific sessions that describe what the high level syntax and API for hash to curve would be for different like curves that you might target. I just looked at one, this alligator2 method for one map to curve thing. It describes basically all of the parameters that you might need to configure for this particular function. What are the constants that are relevant for this like particular function? What are the exceptional cases that you might have to specify when thinking about an API? Like this, there's this other thing called sign of the output, but don't worry about that. And I've truncated some of the like text that follows because from an API perspective, this is kind of, I would say, mostly what you need. Okay. Now let's say you're the implementer and you want to actually like try to implement this thing to make sure that, you know, I can use it for some protocol and interoperates with some other implementation. I again start on the left, go to this map to curve thing, and then I follow the pointers down to like the actual implementation description of alligator2 in this particular case. And it goes into excruciating detail about every single step that needs to be done with like comments as necessary for like the different parts of the pseudocode, noting like, for example, on line 3, like what an exceptional case is that was like described earlier in the syntax and the API. And this seems, and moreover, it's not actually included in the spec, but this is there's almost a one-to-one mapping between this implementation description as written here and the reference implementation that we provided in Sage, not the Sage that was talked about in the previous presentation. And so the ultimate purpose to be like, at each step along the way, minimizing potential source of errors and interop bugs or whatever. So coming back to the original questions, if you were to approach this document and ask yourself, you know, is it easy to use and understand, and will it yield consistent and correct implementations? I'm not gonna like put checks or X's or question marks next to them. You know, I leave it to you to decide as an interested reader. But I offer it to you as a, you know, potential way to think about how we might structure these particular documents. I think this one went through, I spent a lot of time in the group, went through a lot of refactoring and revisions, and I think it does a reasonable job at like striking a good balance. So I may have just implicitly answered these things, but anyways. Okay. Drawing on hash to curve, I think there's a number of things we can do going forward to sort of improve the overall output of the things that we're doing in the Cfrg. And I'm going to enumerate just a couple high-level things without drilling into any specific details, because a lot of it will vary based on like the thing that's being specified, how involved it is, like is it a protocol or not, and so on. I think the most obvious one is to just consider the audience. It should be fairly clear. This is like written technical communication, and that's obviously important for any sort of communication. But that means like making it easy for the audience to like stitch these different pieces of the spec together. So maybe that means like, or that does mean being consistent where consistency matters. Like if you're using pseudocode to describe different implementations of different things in the specification, use the same format of pseudocode at every single step of the way. Don't introduce like one different format for, you know, section A, and then in the appendix use something entirely different. Consistency everywhere will help and will go a long way. And also, like hash to curve does, I claim that like anytime you are using pseudocode, try to make it as close as possible to the actual reference implementation that you are providing with your specification. And we should require reference implementations for these things. But there's a lot of there's been a lot of interesting discussion in various like back channels in terms of like what this reference implementation format should be. Should it be Sage? Should it be Rust? Should it be something else? Maybe that's something we should all talk about. But trying to make them as close as possible is, I think, a admirable goal. And on the heels of that, I would say that consistency sort of beyond like sort of format, consistency in concepts is incredibly important. Primarily because we want to reduce the cognitive load of people who are reading these specifications. So not only like reusing formats, but reusing concepts in the draft itself, but also across drafts. So if we're talking about, say, elliptic curves in one draft and groups or prime order groups in another draft, that could be confusing to people because sometimes they're used interchangeably, even though they shouldn't, but sometimes they are. So being consistent where you can is incredibly important. Using a shared vocabulary for the things that we're talking about is incredibly important. I think for the most part, some of the documents that the Cfrg is working on right now are like, certainly they're internally consistent. I think the review process is such that like it gets a tremendous amount of review in the group before it goes out. Then it goes through like this formal review panel step, and then there's a number of other steps, but I don't remember what they are. And I think like we have reached a level of internal consistency, but external consistency across drafts is it could be improved. And that's a hard problem because, you know, things and concepts change over time. Like what was like, maybe, you know, we used to talk about elliptic curves as, you know, the best thing since sliced bread, but now we want to mostly be talking about like prime order groups instead of elliptic curves. And we want to kind of shy away from elliptic curves in general. So maintaining consistency over time is difficult, but I think for, you know, batches of drafts that are being developed at around the same time, it's not an unreasonable request, and something we could do. Okay, and I think the last one is sort of a call to action, I guess, to embrace formal methods and formality where it's appropriate. There is a tremendous amount of work and referenced and formally verified implementations of especially cryptographic algorithms like Hackspec and Hacklestar and whatnot. Whether or not they're suitable for the, you know, permanent nature of an RFC is not immediately clear to me. But all of this work that basically lets someone take one single implementation and, you know, produce test vectors from it, produce other like implementations in different languages that they can test out, and sometimes produce like optimized implementations as well that are just suitable to plop in production systems. those are good things, and it removes any like chance of potential error from someone implementing these things themselves, trying to interpret an implementation description or syntax description or whatever, and potentially getting it wrong. As I was alluding to earlier, it's like still not clear what is like the right format for this these like reference implementations, be it like something based in Python. The DSA or Rfc 8032 uses Python to describe some of the relevant steps. More recently, things have been using a lot of Sage, just because it's convenient, and there's like been a developing sort of library in which we can use, or developing, I guess you can call it a library of like the specs that are being developed, the building blocks, and drafts are like building on these building blocks and adding more building blocks and whatnot. There's no reason you couldn't do this in Rust or Hackspec or whatever. I think it'd be interesting to experiment with different reference implementations and see what is most approachable from an implementer's perspective, and what is good for really the inclusion in an RFC. Okay, so I want to wrap up and leave some time for questions. So my core point here is that like the work that the Cfrg does, again, is incredibly important. We don't call them standards; they're not technically standards, but I think if it walks like a duck and quacks like a duck, it is a duck. These things should be considered standards, in my opinion. They are incredibly valuable and important to what the IETF and IRTF is doing. And I think we should treat them as such. There's definitely a lot more work that we can be doing, both within the group, even in the IRTF, for producing tooling like Sage, or I forget the name that was in the first one, I apologize, to improve the quality of these specifications. There's like ways that document editors can right now start improving the quality of their specifications through like better prose, better use of terminology, better more consistency, what have you. And I think it's about time that we really took the question of or the task of exploring formal method approaches for Cfrg specifications seriously. And I don't know what that looks like in practice, if it's like a task force to go off and like try to work through these different options, if it's a group in the IRTF to sort of explore this area. I think anything is a reasonable start here, but I think it's given all the work that's been done, I think it's now time to start actually pulling it into the Cfrg. With that, I guess I'll close for questions, if you have any.
All right.
Yeah, Jonathan. Oh.
Thank you very much, Chris. Jonathan.
So I was just thinking, if we are going to have reference implementations and pseudocode, which has precedence, right? If the reference implementation doesn't agree with what's written in the spec, which one do we consider correct? Do we have to decide on a case-by-case basis?
My personal opinion is that we should have reference implementations and no pseudocode, but that's just not the way specs are published right now. We have pseudocode to describe the things, and reference implementations sort of hang off the side of them. It would be great if there was like one clear, correct description of what the thing is and how it's implemented, not two possibly inconsistent representations. So yeah.
All right, thank you. Thomas, I guess you're in the room.
I didn't sign in. If you don't mind,
Thomas is in the room, but there's other people in the queue, so I guess Nick, go ahead.
Oh, okay. So what about producing non-informational drafts within the Cfrg? Is that completely out of the question?
No, I don't think so.
Would you be a proponent for that?
I like, does it? I don't think so. Whether or not that would I mean, the topic of like, should the Cfrg be in IRTF versus IETF has come up before. My general stance has been like, if it's not broke, don't fix it, like from a IRTF versus IETF perspective. But I can't see any harm from like rechartering to potentially, you know, explicitly include like non-informational documents.
Okay, thanks.
Yeah, I mean, there are procedural issues there, but in practice, Cfrg should be producing as good a quality document as it can. And yeah, we can have the arguments about whether it should be an IETF or an IRCF group later. Thomas.
I guess I'll go. Shivan Sahib, Brave. This goes to a discussion that we were having on Slack, Chris, about security proofs. And like, do you think there's a conflict between the proof and implementation complexity or simplicity? Then like, what should you do? And maybe you can say in the draft, like, go and look at this other place where we did something slightly different and then proved it. Yeah, just wondering what.
I think anecdotally, like the security proof should trump everything. If the implementation doesn't match, there should be like a very clear reason as to why it doesn't match, perhaps with like justification as to why it would deviate from what has been analyzed in practice. But I think we should strive very hard to keep like all these things consistent. And I would include like the security model and the analysis that's been done as part of like the description of the specification. So yeah, keep everything consistent.
And hi again, this is me, Tommaso Pecorella, and for real. Anyway, I'd love to have a specification written like you said. I'd really love it. I have mixed feelings about reference implementations because I fear that for some cryptographic algorithms, having a reference implementation would lead to more errors than a carefully written one, meaning timing errors or stuff like that. Possible timing attacks. I mean, somebody that just grabbed the reference implementation, transform it in another language by some mathematical methods, doesn't use the brain, and go on. I would love to have, however, some test cases. Like if these numbers are there, you must reach this point. Because I fear that in some cases, this could be more useful to debug or test case your particular implementation.
I mean, yeah, I certainly agree that the test cases and test vectors are invaluable. And I think most of the specifications that I'm aware of include
both
them.
Probably would be the best.
Yeah. In terms of like whether or not reference implementations should exist, that it was actually an explicit choice to use something like Sage to describe these like hash to curve based drafts, because you can't just like easily take Sage code and plop it in production. We wanted to make sure that was like something you did not ever do. And furthermore, we took steps in the reference implementation to try to describe, or avoid sort of, I guess, implementation pitfalls. So for example, if you need to do like a comparison of two like byte strings in constant time, we didn't just like in Python say like, does A equal B? We would say like, if A is equal to B constant time, I forget like the extra string, but like you make it very clear, like, this is how you would actually implement it in practice. But I mean, it's a good point. Like, should reference implementation exist? No. I tend to think they're useful,
if
but
you
I guess it
can
depends.
write a reference implementation that cannot be used as it is by, let's say, an undergraduate student that doesn't actually have time to actually do something right, that would be great, and I'm all up for it.
Yeah, I mean, I guess the other side of that coin is there are projects like, like the recent NIST PQC competition, all the reference implementations there were actually very high quality implementations, and they perform very well. You could reasonably take some of those and plop them in production if you were, if you wanted to do so. And I guess it depends on, what sort of bar you hold for, the reference implementation.
I guess it
quality.
also depends on how long you want to have the RFC and how long is the code.
Yeah, of course.
Thank you.
Yeah.
Hey, this is Max. Great talk. I just want to say I've found at least one protocol where not the pseudocode, but the English language text did not match the reference implementation. Not an IETF one, but one from outside. So that can happen too. I do think it's maybe a good idea to be worth considering to say what should be, as somebody else mentioned, like believed if there's a discrepancy, right? So the spec could maybe say, if there's a discrepancy between this and the implementation, you should always fall on the side of, I don't know, whichever, right? And that way you have it be unambiguous. So maybe that's something worth.
Yeah, that's not a bad idea.
All right, thank you very much. Just to follow on from that last point, I think it's very, very clear that Chris had some great examples, but this is very much not a Cfrg specific set of problems. There are ambiguities and issues with all of the specifications. And certainly looking at the dependency graph Colin Jennings has for the WebRTC specifications and the sprawling mass of documents there, I think it's clear this is an issue of consistency that we have in many different parts of the community. So what I've been trying to do with these talks is to sort of try and stimulate some discussion, try and see if there's interest in research on protocol specification, thinking about how we specify protocols in the IETF and the IETF communities, and starting to think about what are the research challenges in effective protocol specification and how we can improve the way we specify protocols. There's certainly been a lot of discussion in the chat and a lot of really good questions to the talks. I think there were 3 fantastic talks there. So thank you everybody for both giving the talks and for the discussion in the chat. I am certainly looking to gauge interest to see if people are interested in potential IETF work in this area. If you are interested in this, please do talk to the speakers. Please do talk to me. And if you would be interested in following up on this, put your names into the document that's linked on the slide, and I just put in the chat. And we're, normally I would arrange a lunch meeting or something at the IETF. In COVID times, that's obviously a little bit difficult, but please do put your names in the chat. We'll arrange a call at some point if there's interest, and see if we can take this further. So thank you again to everybody. Thank you to the speakers. Thank you to everybody for paying attention. If there are any final questions, I'm very happy to take them. And if not, thank you again. All right. Thanks, everybody. And look out for the ANRW call for papers for next year.